Test. Hello.
Is my mic? There we go. All right. I am going to talk about IBC and public-private blockchain interoperation. I'm Chris. I lead research on IBC at the Tendermint company. And I want to make sure I don't shortchange you because this was billed as a workshop. It's a bit difficult to do a workshop without a whiteboard, so we'll make it an interactive presentation. If you have a question about a slide, raise your hand. I'll stop and answer the question. Jack, what's your question? What does IBC stand for? Great question. IBC stands for, this is on my slide, no, inter-blockchain communication. And we'll talk about which chains are communicating, what is going between them, and what we mean by communication in just a few slides. So, what will be in this presentation, and what might you want to ask questions about? The design goals of IBC as a protocol, what the implementation looks like, what actual data is flowing around, to where is it flowing, from where is it flowing, and how is it being authenticated. How you might do IBC yourself, and we'll walk through an example of IBC used to interoperate between public or sort of transparent chains like Bitcoin or Cosmos or Ethereum, and shielded chains like Zcash. Then I'll take any questions, but I'll also take questions throughout the presentation. Again, just raise your hand. There we go. I did put the name on a slide. What is inter-blockchain communication? At the base layer, inter-blockchain communication is a way to relay data packets between two chains, which we call A and B. Those names don't mean anything. You could also call them B and A, but we keep it alphabetical to make it less confusing. Off-chain relayers, so processes running and watching the chains, maybe full nodes, maybe light clients, are responsible for the physical transmission of data. So they need to have an actual link layer as a fiber cable or something. But we're really talking about, at the conceptual layer, of blockchains communicating with each other. Blockchains communicating with each other means that there needs to be authentication involved, which I'll talk about in a minute. A key part in understanding where IBC sits in the protocol stack is that to IBC, the data payload is opaque. You can think of it as roughly analogous to TCP/IP. IBC sits on top of blockchain, so it's something that a blockchain implements, just like a computer or a networked computer implements TCP/IP, but it sits below the application. Just like TCP/IP doesn't define what HTTP is or what a website looks like or how it's rendered in a browser, it just defines how to get the data from point A to point B and how to ensure that you're getting the data you thought you were getting and you're talking to the person you thought you were talking to, and that you get the data exactly once. IBC also does those things. So how do we authenticate? The idea is that we want each blockchain to run a sort of client of the other blockchain. You might have heard of Bitcoin SPV or a light client running on a phone, like a Feather developed by Parity. Those light clients are executing some special kind of verification logic, usually on part of the consensus transcript of the consensus algorithm which the chain was running. So if you have a Tendermint chain or an Ethereum chain or any sort of blockchain, there's some underlying consensus algorithm with messages being relayed between nodes, usually involving signatures in the case of proof of stake, or particular hashes of blocks hitting targets in the case of proof of work. And that transcript, if the consensus algorithm designers thought about it beforehand and designed their consensus algorithm well, can be summarized, compressed, and then transmitted to a light client, which is usually connecting every so often and doesn't have tons of bandwidth, and verified by the light client in a way that still preserves the protocol rules or the important protocol rules of the consensus algorithm. So that the light client will be convinced of a particular consensus execution transcript and result, so like some part of state of the blockchain, only if, in fact, the blockchain had come to consensus in that state. So only if that chain was a chain of a particular height on Ethereum, or only if it had been finalized in the case of Tendermint. So IBC layers on top of that. It requires that blockchains each run light clients for each other, and also checks particular parts of state. Each chain allocates a certain part of state for the IBC protocol, and in that part of state keeps some queues of outbound and inbound packets. Those queues can be verified by the other chain. The second chain, chain B, when it's running a client, is verifying outgoing packets on chain A. The different words. Yes?
Does it? Oh, wow. With microphone. does it mean if I have multiple chains I want to talk to, I have to run, or this chain has to run A through Z light clients? Or is that just like one light client for IBC and that does the resolution for other chains?
That's a great question. So as I'll talk about it today, the IBC protocol is defined between two chains. So the answer to your question would be yes. If you want your chain to connect to 50 chains, you have to run 50 light clients. Now that might be pretty inefficient, especially if some of those connections are only being used every so often. So we're also building into the IBC protocol multi-hop routing, so that you'll be able to, say, route through the Cosmos hub, and in a few different ways with somewhat different security properties, either use the client on the Cosmos hub or physically send the packets through the Cosmos hub and only run one light client for the Cosmos hub, and maybe one client for the hub and one client for your favorite other chain, and then route your other packets through those existing connections. I won't talk about that too much, but you can see if you define a protocol hub between two chains, how you could start routing packets multi-hop. So a key part to understand how IBC looks from a security perspective is that we're trying to impose no additional security assumptions in the base protocol other than that of the consensus algorithm, modulo whatever the light client does. So if the light client in Tendermint, as Tendermint light clients can actually verify finality of blocks, you have very strong assumptions in order to break IBC here, so to speak, in order to break the rules that the protocol provides to applications built on top of it. You would need to fool a light client, which means that someone had equivocated and someone would get slashed. The rules can be different. IBC is built to work with a variety of different consensus algorithms and light clients. So you could have some kind of light clients which provide stronger guarantees and some kinds which provide weaker guarantees. But the stronger guarantees you have, generally the better. So why might you want such a thing as IBC? A very basic thing you can do is transfer tokens in between two chains. This will probably be the first demo application. Both fungible and non-fungible tokens. And in the example, I'll cover the specific atomic steps involved in doing that. But the protocol itself doesn't have anything to say, IBC that is, doesn't have anything to say specifically about tokens. That's just an application. Other applications get more general. You could have, you could run some kind of atomic swap, although IBC is not necessarily the best protocol for doing that. It can be used for atomic swaps. But you could also run much more complex kinds of contract executions across chains where you reason about your contract as a compositional object with state stored on multiple chains, and you can relay messages just like you might relay messages between a set of Ethereum contracts, then reason about the state of all the chains combined. You might use IBC as a transport layer and authentication layer on top of which to build an object capability system like what Agoric is working on, which can provide even stronger guarantees about how capabilities can be passed around different contracts and how faults in contracts can be limited in their impact upon the rest of the interconnected ecosystem. You can use IBC, and we haven't done this yet, but you can use IBC as a compositional building block on top of which to implement sharding protocols, where you have mutually comprehensible virtual machines. So say you're running multiple chains with the EVM or multiple chains which can run WASM code, and you're relaying contracts between those chains according to some load balancing algorithm. I want to be clear that IBC does not require mutual comprehensibility. So a traditional sharded architecture is going to feature the same VM running on multiple chains, and IBC doesn't need that. It only requires that the part of each chain implementing the IBC protocol talks the same IBC protocol, but otherwise the state machines can vary. But you could also use IBC for sharding. The specific example I'll give of two varied state machines is using IBC to send tokens from a Cosmos zone, or maybe the Cosmos hub, to the Zcash chain, shield them on the Zcash chain with sapling, so using ZK-SNARKs rather, and then once you're done shielding them and transacting in private ways, send them back to Cosmos through the IBC bridge. So, the security model IBC is trying to provide as a protocol in providing authentication and exactly once message delivery is allowing you to preserve contract invariance across chains. So if you think of the simple case of transferring tokens, what we care about with a token, are a fungible token, are really two key properties. We care about fungibility, so we care that each unit of this token, and often they're subdivisible, so each smallest unit is identical. It can be exchanged for another unit. There's no difference between these units. And we care about fixed supply, so the token needs to be scarce. If I could just mint new tokens whenever I wanted them, it wouldn't be very useful. IBC allows us to reason about a token, a logical entity, as a sort of representation in multiple chains at once. So if you create a token bridge or a token peg, and there's some slight differences in how they're implemented and what they're called, but this idea in both cases is that you're reasoning about a token, a single logical token, as a split state representation where some tokens are stored on each chain, but the balance sums to a constant. So if we think about how we might do that, given the ability to authenticate packets and to send packets exactly once, we simply transport the tokens in the packets, conceptually speaking. So when we send a packet from chain A to chain B, when the user wants to transfer tokens from chain A to chain B, before we send the packet, we burn or we escrow some tokens, depending on the kind of peg. That amount of tokens, along with the denomination, is stored in the packet data. The packet is relayed exactly once to chain B, and then in chain B, the packet is unpacked, interpreted in token quote-unquote vouchers, are minted corresponding to the amount and denomination of the tokens we just burned. So we burn tokens here, we minted tokens here, the amounts were the same, so the total supply is constant. And the way that can be verified is on A, when that packet is sent, the state machine writes a particular value to a particular key in the store. Then when headers get sent to B, B verifies using its light client the consensus transcript of A. B can verify that that particular value was written to the store, check that the amount of tokens in that packet that were sent, or the amount of tokens the user is trying to redeem, the amount of vouchers the user is trying to redeem on chain B, in fact mint those tokens and send them on to the user, who can then do whatever they want. So, to allow, we want to reason about modules on different chains talking to each other, so we create two abstractions called connections and channels. Connections represent authentication links between chains. So in order to create a connection between two chains, the two chains must exchange client information so that they can verify each other's consensus algorithms. When you open a connection, you provide what we call a root of trust, or a consensus state. The root of trust gives some state of the consensus algorithm of the other chain, so it's subjective. You have to have some procedure for initiating this. And then from that consensus state, you can verify future blocks finalized, verify future blocks appended to a chain, in the case of Nakamoto consensus. Whatever your consensus algorithm is doing, that initial state is what allows you to verify future states, future segments of the execution transcript, and verify future packets sent or received on that second chain when the IBC handler actually verifies the state. Now, in some cases, bad things may happen. And from the perspective of designing a protocol for connections between many chains in a complex topology where Cosmos might be connected to Polkadot, might be connected to Agoric, might be connected to Ethereum, we want to contain faults. So we do this in a few ways. Some of the ways are at the application layer by measuring how many tokens are sent through a particular IBC channel, for example, or by doing similar things with contract execution to check the faults. Some of them are at the consensus layer. If we can detect a consensus equivocation, we can sort of freeze the connection, prevent further packets from being sent, and thereby contain the damage. But there are a few different ways that a connection can be closed. So on top of a connection, when two blockchains have exchanged consensus states and have the ability to verify each other's future consensus progress, we can then pass messages. Those messages on what we call a channel as an ordering abstraction are absolutely ordered in the sort of default IBC implementation. Future implementations might have unordered channels, and they might have partial ordering with DAGs, but we won't get to those yet. That's fancy. The simple implementation, and all you need to understand from the conceptual level, has messages ordered in an exact order. So if you send a message on chain A, then another message, and then another message, call those 1, 2, and 3, then on chain B, the only order in which message receipt will be allowed is in the same order, 1, 2, 3. That's because the handler on chain B, the IBC handler, can check in which order chain A executed those packets and ensure that it receives them in the exact same order. So using that ordering, we can reason based on which order we executed actions, such as sending tokens on chain A, about which order we'll execute the corresponding actions associated with receiving those IBC packets on chain B. We use counters to prevent replay, just like nonces in signatures from accounts on Ethereum or something like that. And each packet, which is sent to send tokens or to execute a cross-chain contract call, the packet is the atomic data unit, which is being relayed between modules on two different chains. Each packet keeps track of the source information, the chain which the packet is coming from, keeps track of the destination, the chain and module to which the packet is going, has a sequence number and some other metadata to prevent replay, and has data, which to IBC is opaque. In the case of token transfers, data will contain a denomination and amount. In the case of cross-chain contract calls, it would contain a function signature and encoded parameter data. In the case of some kind of complex sharding mechanism, it would contain actual code, which is then to be executed on the destination chain. The IBC protocol guarantees nothing about what that data is or how it's encoded. That's up to the application. All IBC guarantees is that the packets are authenticated and they're sent exactly once in order. Now, things could go wrong. And some of those things we really can't do anything about. When you use IBC, you're trusting, or so to speak, you're making the usual assumptions about the consensus algorithm of the chains you're sending from and to. So if the destination chain is Byzantine and commits two different histories and it forks, for example, you don't have any more guarantees than you would have in the usual case of that chain forking about what will happen. But there are some cases we can guard against. One of those cases is a particular kind of lack of progress, which we'll call censorship. So it may often be the case that the destination chain is live, it's making blocks, but it's not confirming the transactions necessary to receive IBC packets. For example, many blockchains which need to charge for code execution have some sort of gas market. So transactions are chosen from the mempool and by the validators or by the block proposers and included on those chains based on whether or not they paid enough fees for gas. So if an IBC packet was relayed where you didn't provide the relayer or the user didn't provide enough fees to pay for gas, that packet won't get confirmed in time. And in the case of that happening, we want to provide strong guarantees to the application using IBC about the way its invariance can be preserved. If the packet wasn't confirmed on chain B, now these tokens, if we were sending tokens, are in this ephemeral packet. They're available neither to the user on chain A or on chain B, and that's pretty bad. Now we've violated our total supply conservation because the user can never get their tokens. So we want to allow timeouts. If a user can prove that chain B has made progress, but has continued to confirm blocks, but has not included a particular IBC packet, we want chain A, the module on chain A, which sent the packet, to be able to revert, essentially, or undo whatever execution was involved in sending that packet, and in the case of coins, return coins to the user who was originally trying to send them. Then the user could try again, they could give up, we don't really care. The IBC has provided the guarantees to the application, which the protocol layer could provide, which is that this packet is timed out, the state execution can be reverted, and if it ever, in fact, is received on chain B, it will now just do nothing because that's past the timeout had. Does that make sense? So, question?
It doesn't make sense. It doesn't make sense. I'm just wondering, because the rollback on chain A, it's going to be super application specific, right? I mean, a simple coin transfer, you just change the balance, but like I minted an NFT here, transferred over there, and I continue, like how does chain A know, like, to not do anything until the timeout has passed, or you know what I mean? Does it make sense?
Yeah, so this is going to be application dependent, and what the module on chain A, what that module ought to do is dependent on the guarantees it wants. So in the case of token transfers, if you're transferring tokens from chain A to chain B, timeouts of independent packets are causally independent because they're sending different tokens. So if packet 2 times out, but packet 3 gets confirmed, that's fine. You just give the user back the tokens associated with packet 2 and the tokens associated with packet 3 were sent to chain B. But if you're doing something where you need perfect logical sequencing, where you don't ever want packet 3 to be confirmed and packet 2 is not, then you'll use a kind of ordered channel where a timeout will close the entire channel, then you have to try again. Yeah?
So these timeouts assume that to have reliable timeouts, we are assuming that both chains have some sense of time and that their clocks will not drift relative to each other too much.
No. I mean, you could do timeouts that way, but at the moment we think that would be pretty unsafe. So what we do for this kind of timeout uses a block height. And specifically it uses the block height on the receiving chain. So if I send a packet from chain A to chain B, there is on that packet a specific timeout height. That was the metadata I was talking about. And that timeout height is some number referring to the consensus height of chain B. So let's say it's 10,000. Then one of two cases happens. Either chain B executes that packet before height 10,000, in which case tokens are released, everything goes smoothly, or height 10,000 passes before chain B executes that packet. If the latter case happens, then you can now prove on chain A that chain B has passed height 10,000 without executing the packet. And then you can send the coins back to the original sending user on chain A.
How do you do proof of non-exclusion of an IBC transaction? Proof of inclusion seems intuitive, all cryptocurrencies do it, but this seems to need a proof of non-exclusion of this IBC packet.
You mean non-inclusion?
Non-inclusion.
Yeah, okay. Yeah, non-exclusion is inclusion, I think.
Yeah.
I don't know. So a proof of exclusion, yes. And one requirement of IBC is that the commitment system provided by the state machine, so a Merkle tree, or the IAVL tree specifically in the case of Cosmos, can provide proofs of exclusion. So you would provide a proof that a particular sequence numbered packet, the packet that you're trying to time out, has not been committed on chain B. You would say that this key in state doesn't have a value. And you know that that key in state would have a value if the packet had been committed, so since the key in state doesn't have a value, the packet cannot have been committed, and you can safely release the original asset. So there's no subjectivity involved in this time. You could also use, under some constraints, you could use the wall time, like a BFT timestamp on chain B, as long as it always increased, as the logical time as the block height went on. But for now, we're probably going to stick in the first version of block heights.
Thank you.
So, in the case of token transfers, what utility to the topology of interconnected chains does this provide? Assets in chains become independent. If you have an asset on one chain connected to a set of IBC interconnected chains, that asset can be used on any other chain. So you can sort of choose your state machine and your assets independently. While choosing it independently and using the benefits of each different state machine, you get the guarantees the asset originally provided. So if you transfer Bitcoin or Ethereum tokens through Cosmos, through the IBC to chains, which could be Cosmos chains, it could be other chains connected to Cosmos chains, that can always be, assuming the chains behave as expected, that can always be redeemed back through some path to the original Bitcoin. So you retain fungibility while gaining the features of all these different state machines for the original asset. And in order to build that into a large network topology, we're going to engineer some kind of multi-hop routing, which is out of the scope of this presentation, but you can think of it very simply, and you could even do it at the application layer in this case, just by sending tokens from A to B, from B to C, from C to D, and then when you're done doing stuff on D, sending them back through the reverse path, D, C, B, A, to get your Bitcoin if chain A was Bitcoin. Another key point to emphasize about IBC is that the protocol is maximally permissionless. So by default, IBC does not constrain which chains can talk to each other chains. As long as someone is willing to pay the gas cost to set up a client to track consensus state and to receive and send packets, chains can connect to each other as they like. Now, there are probably going to be restrictions at the application layer. The Cosmos Hub doesn't want to allow any other chain to connect and suddenly start minting atoms. That would be terrible. But what the Cosmos Hub might do instead is allow any other chain to connect and prefix any token sent by that chain with the chain identifier. So then the protocol itself doesn't provide permissioning, but users inspecting the state decide which tokens, prefixed by chain identifier, they think are real and which they think are some scam nonsense. Is that a question, Alistair? No. Okay. So this allows you to use new features with, in a key sense, old security and old assets. In a particular case of interest, you could, if we connect Zcash to the ecosystem of IBC interconnected blockchains using something called a peg zone, which I'll talk about in a minute, you would be able to achieve shielded privacy for existing assets by using the sampling circuit in Zcash, so the ZK-SNARK circuit with proofs of fungible asset transfer for existing assets which have been transferred to Zcash using IBC. The other benefit you get in this particular case is that you can impose restrictions at the channel boundaries, so impose restrictions between chains which are talking on IBC that allow you some introspection into state. So in the particular case of tokens, you can track the supply of a token, the amount of a token transferred through a particular IBC channel between two modules on different chains. So if you connect a Cosmos chain to Zcash and you want to send some tokens from Cosmos to Zcash and do some stuff on Zcash, play with them as shielded tokens and send them back, you could track nothing, but that would expose you to inflation bugs. And in fact, Zcash discovered at least maybe a year and a half ago, but publicized only a few months ago, an error in the original trusted setup used for, or the sort of trusted setup associated with SNARK construction used for the circuit in version 1 of Zcash that allowed anyone to mint coins. They think that no one did this, but if you wanted to connect the chain to Zcash, you might be well advised to track the tokens going in and out so you can ensure that no more tokens are ever sent back out of Zcash than were sent in the first place. And you would be able to do that by, in this IBC channel, keeping a running counter of the tokens in and out, and making sure that if somehow someone actually tried to send more tokens from Zcash back to Cosmos than had been originally sent back in, something's gone really wrong, there's an inflation bug, close the channel and figure it out. Another feature of IBC, which I'm particularly excited about in the future, is in a sort of opt-in upgrades. If someone wants to launch a friendly fork, a new version of a state machine with some changes that might be controversial or risky, they can launch it and allow anyone to connect over IBC. In particular, also using a protocol which we're working on called interchain collateralization, where validator sets can be partially shared between chains. A new chain could change some features of the Cosmos Hub, maybe convince some subset of the Cosmos Hub validators to validate, launch the chain, pay a bit back for the interchain collateralization, and convince everyone slowly to switch over to the new version without requiring a risky change in the whole state machine at once. So to talk briefly about what's required for IBC. The reason I bring this up is that IBC is a protocol designed to be used between Cosmos, certainly, but also other potential blockchain stacks like Polkadot, and we've tried to impose the minimum set of requirements on the implementing consensus algorithms and state machines. So IBC needs, for one, finality. You need, in order to send packets between two chains, you only want to send a packet to the second chain from the first chain when you finalized a particular state on the first chain. If the first chain was Bitcoin and later on it ended up choosing a different fork as the longest chain, and you had already sent the packet, that would be pretty bad because you can't take the packet back. So IBC requires finality. Tendermint certainly provides this. Anything in the PBFT class will, Grandpa from Polkadot will provide this, and we hope IBC will be functional there as well. Other consensus algorithms, Hot Stuff, recently released, quite interesting, provides finality. Casper FFG, perhaps whatever variant ends up being used in Ethereum 2. For Nakamoto consensus chains, such as Ethereum, Bitcoin, Tezos, or Ouroboros Preos, or Genesis, you have to create what's called a finality gadget if you want to use it with IBC. You have to choose some number of blocks, just like effectively you do as a user when you use Bitcoin. When you're accepting Bitcoin for a Ferrari, hopefully you choose a large number of blocks. So in case you can be relatively assured that that transaction will not in fact end up being reverted, you having already given away the Ferrari. Just like that, in IBC you need to choose some number of blocks, n equals 6, n equals 50, after which you will consider a chain of that, transaction of that depth from the chain finalized, and you can act upon it accordingly, sending and receiving packets. The second thing IBC requires is some sort of Merkleized state with proof verification. So you need to add your unspent transaction outputs or set your key value pairs in state in a way that the light client running on the other chain can verify inclusion or exclusion of particular key value pairs in that state. The client only needs to verify a subset, the subset associated with IBC, stating that channels have been created or packets have been confirmed or packets have not been confirmed, but it will need to verify that in the state machine of the receiving chain. So in order to bridge a probabilistic finality chain like Bitcoin or Ethereum with the interchain network, with chains with finality running, say, Tendermint, we create what's called a peg zone. This is because we assume that we can't modify the Bitcoin and Ethereum state machines. If we could convince the developers of Bitcoin to include IBC in Bitcoin, we could just do that instead. But I think that is an unachievable dream. So instead, we'll build a federated peg. A federated peg, with some different variants with different kinds of slashing, requires no changes to the Nakamoto consensus chain. In the case of Bitcoin or Ethereum, a federated peg consists of some kind of multi-signature account, where the validators of the peg chain, or the peg zone, are also key holders of that multi-signature account. When transactions, IBC packets, say sending coins, are sent through the peg zone to the Nakamoto consensus chain, that federated peg key holder set is responsible for signing those transactions and sending them to Bitcoin or Ethereum, and vice versa. It's responsible for sometimes running a light client to the Nakamoto consensus chain, but attesting that transactions have been sent, say, containing tokens, back from the Nakamoto consensus chain through the peg zone to the rest of finality featuring Cosmos chains, particularly IBC. There are different ways you can implement the mechanics of the federated peg with different security properties. The simplest is some kind of just threshold signature account, which both Bitcoin and Ethereum support. You might want something more complex with fault attributions than you would need like a multi-party ECDSA protocol. And you probably also want some sort of economic incentivization, both for the validators of the peg zone to sign the transactions they're supposed to sign, and for them not to sign the transactions they're not supposed to sign. So somewhere, be it on this peg zone or be it on the Cosmos Hub, somewhere you want slashing conditions for the key holders of this peg zone behaving in Byzantine ways, where Byzantine ways are defined as ways which contradict the protocol according to which they are supposed to relay transactions between the peg zone and the probabilistic finality chain. Once you build one peg zone for a Nakamoto consensus chain, appropriately secured for the use cases you intend to use it with, that peg zone can connect to any other chain using a standard IBC protocol, since it has finality running Tendermint, the other chain has finality with Tendermint or Grandpa or whatever, and act as usual. So you only need one peg zone to create this bridge between the probabilistic finality chain and the rest of the Cosmos interchain network. So a specific example with a peg zone and using token transfers is bridging Cosmos, the SDK.coins type, which is a fungible token, multi-denomination coin storage, to what's called a user-issued token on Zcash. So Zcash user-issued tokens are a proposed specification for an ERC20 style fungible token implemented on Zcash with support in the Zcash shielded Saptum circuit, such that if you have those tokens on Zcash, you could shield them, unshield them, and send them around privately, just like you can send Zcash, the native asset, around on the Zcash chain. Using IBC, what we want to do is to peg those tokens to peg tokens on a Cosmos chain in the SDK.coins type, such that you could send those coins from Cosmos, from any chain connected to say, the Cosmos hub, using IBC, to Zcash through the peg zone. You could do your secret transactions on Zcash, then you could send them back when you were done to Cosmos. So you can think about, if you want a very concrete example, you could do this with atoms. Maybe you could do it with photons in the future when photons exist. Any other token that exists on the Cosmos hub and is connected through some sequence of chains, you could use this protocol with. We do this by creating a bipartite association graph between denominations on the Cosmos chain in SDK.coins and denominations on the Zcash chain in user-issued tokens. So we could call it, if we were mapping to Ethereum, we could call it IBC/Ethereum, but that's a bad example because we're mapping to Zcash, so we would call it IBC/Zcash/ some user-issued token number, and on Zcash, each user-issued token number would be associated with a particular name in the SDK.coins type on the Cosmos chain. How do we do this? We have a dedicated, that should say module on Cosmos. We have a dedicated module on the Cosmos chain that holds these coins in escrow when we send them to Zcash. And it interacts with the IBC handler such that when packets are sent to transfer the coins are sent through the module interacting with the IBC handler atomically with the send packet sending those coins to the peg zone. The peg zone will verify the proof that those coins have been escrowed on the Cosmos chain, and it will send a transaction using the multi-signature account to the Zcash chain to mint the user-issued token vouchers in the same amount and the associated denomination. So we have some bipartite graph mapping the two denominations. That bipartite graph is tracked by the peg zone, and the peg zone uses it to determine which user-issued token denomination it should create when coins are sent from Cosmos. Now the user-issued tokens are on Zcash, so when the user sent them from Cosmos, they provided an address on Zcash at which to receive them. Now they're controlled by the user, and the user can do whatever they want. They can keep them on Zcash forever, they can send them around, shield them, unshield them, pay for things, etc., send them to another user. Then, whenever they're done, whoever they're owned by now on Zcash, if that owner wanted to send them back to Cosmos, they would take the reverse path. They would burn the user-issued token, so this is a proper peg. So we have a source chain, which is Cosmos, and we have a pegged token representation on Zcash. So they would burn the user-issued tokens on Zcash, submit a proof of burn to the peg zone. The peg zone would verify by running a SPV client for Zcash, verify that those user-issued tokens have been unshielded and burned, and it would send a packet back to the Cosmos chain to mint the associated SDK.coins denomination using that bipartite association graph, and release it to the user who would send them back from Zcash. Basically just like that. So, what are some properties of this construction? One, it's permissionless and opt-in. As soon as this peg zone exists to bridge, Cosmos and Zcash, users can transact through it or not transact through it as they like. Many people were, I think, justifiably concerned about the novel cryptography used in Zcash and might not want to expose their tokens to inflation risks. Because the amount of coins transferred through the peg zone of each denomination can be tracked exactly, any user who doesn't choose to use this bridge isn't exposed. So if, in fact, there is some sort of inflation bug, or you can think of it more generally, if I'm, as a user, using a chain, transferring some assets to another chain through IBC, and something goes wrong on that chain, I may be screwed, but I chose to take the risk. Users who didn't choose to take that risk will be, assuming the application level is implemented correctly, will not be exposed to any risks by malicious behavior of that chain. So there is trust, but the trust is chosen on the behalf of each user. It's not chosen by the protocol. You have IBC connections between many chains, and you as a user choose not to use them, you're never exposed to any risk. Another property of this implementation is that it provides full privacy. So if you transfer your tokens through the Cosmos peg zone, they're transparent. They're transparent until they get to Zcash. On Zcash, they can be shielded. And then they will enter into the shielded pool. You'll have the anonymity set associated with the amount of that particular denomination that have been transferred to Zcash and unshielded. You can transact in that. Hopefully, assuming enough people are using it, it will be a quite large anonymity set. And as long as people want to use it, it can remain on Zcash. As soon as they want to send it back, they unshield it so it becomes transparent again, and they get it back on Cosmos. It's also quite scalable. You only need one peg zone to Zcash. That peg zone can handle any number of denominations on the Cosmos side, on the Zcash user issued token side, and it works with the existing gas mechanisms, fee payment schemes for those chains. So, in the future, what might we add to IBC? One thing we might add are higher assurance proofs. The correctness of IBC is dependent on the correctness of our light client verification algorithm. Our light client verification algorithm tells us that a block's been finalized that is actually not. IBC could receive packets multiple times, it could break. So we require that the light client verification algorithm actually tracks whatever the consensus algorithm of the source chain sending the packets, and vice versa of the receiving chain in case the packet's back the other direction. It tracks what that consensus algorithm is doing accurately. If we're using a peg zone connecting to a Nakamoto consensus chain, the degree of assurance we have is proportional to the number of confirmations we wait before we consider a particular block final. If we're connecting to a Tendermint chain or a finality gadget chain, the degree of assurance we have is proportional to the cost that would be required to subvert that finality. So in the case of Tendermint, more than a third of validators would need to be Byzantine and would have committed an attributable fault in order to fool a light client, which IBC runs. So we have a pretty high, corresponding also to the amount staked, a pretty high degree of assurance that we're only behaving as a light client correctly. You could get an even higher degree of assurance, however, about consensus algorithms and about particular parts of the state machine if you had more advanced verification. By default, IBC does not require cross-chain state machine comprehensibility, like I mentioned, except for the little part that's implemented in the IBC. So if you wanted more assurance that some code on another chain was getting executed in a particular way, you might want to create a specific proof for, say, the execution of some contract, and relay that over IBCs that the IBC client on the receiving chain could check that not only had the packet been committed, the associated state transition had been executed correctly. You might even want further assurances with some sort of fancy recursive SNARK construction where you verified from Genesis that the whole sequence of state transitions in a recursive SNARK, like what Coda is working on, that could be verified in an IBC connection, which I think would be quite interesting in the future. Still need to solve some other problems, like if you track Nakamoto consensus, you need to track multiple potential forks. But another direction of research is in Byzantine recovery. So if consensus breaks at the moment, IBC freezes, in the default protocol, freezes the connection to the channels, prevents any further asset transfer, and says, invoke Deus Ex Machina. Deus Ex Machina, in this case, is governance or it's social consensus. So the governance, many chains using IBC will probably have governance systems, and those governance systems could choose to execute some irregular state transitions and try to restore assets to the people who originally owned them, somehow correct whatever happened according to this Byzantine fault. Or humans could look at the many interconnected chains, see what happened, decide to make irregular state transitions themselves in their local databases, then fork the blockchains. But there could be other useful things we want to do. If in the case of attributable Byzantine faults, I don't know if you can hear me with the siren outside. Okay, in the case of attributable Byzantine faults where a loud siren goes off and the chains can check that in fact the fault has occurred, you could tell modules that, and the modules associated with who are sending packets and receiving packets through IBC could take appropriate action. Maybe they could verify parts of state on different chains. They could try to release assets to users. They could provide some weaker some weaker guarantees like assume synchrony and then allow users to release assets if some time has passed as nothing has happened, stuff like that. So, thanks for the questions throughout, but I will now take any questions at the end about any part of this presentation or about IBC in general. We are working on specifications between already a multi-stakeholder group, particularly the Tendermint company, the Interchain Foundation, and Agoric. Anyone who's interested, please contact me. You're totally welcome to join the IBC calls. They're also recorded and put up on YouTube. The specification is at github.com/cosmos/ICS, which stands for Interchain Standards. You can email me, cwgoes@tendermint.com. We currently have groups seriously interested in implementing IBC in 4 languages: Go in the Cosmos SDK, JavaScript, Rust, and Haskell. So if you're interested in implementing IBC or have a request, also let me know. Questions?
If no one has questions, then a warm round of applause for Chris.